Hello everyone, welcome to In 5 Minutes. In this video, we are going to see the application of double integration, that is mass of lamina. So till now we have used the double integration to calculate the area between the two curves. So now we will concentrate how to find the mass using double integration. So mass of lamina is nothing but it is a mass of two-dimensional figure. So what is density? Density is nothing but mass upon volume. Okay, we have to find this mass, but we have to use the double integration. So density is mass and volume is nothing but area into height. Let's say if we have the cylinder, which is a three-dimensional figure, whenever we have this type of cylinder, we can find the volume as surface area, that is the surface area into height, that will be our volume. So here we can write density is mass upon area into height. So from here we can calculate mass as density into height into area equal to mass. We know the formula of area in double integration. This density into height will be some other variable density, which is known as mass density function. Okay, so this density is different from this density because this density has also height. Okay, so this is a mass density function. So the mass of lamina is nothing but area, that is double integration over region R dx into dy. This is the formula of area, but here we will also have another term, that is mass density function. So if we solve this double integration, we will get the mass of lamina. So mass of lamina, in question we will given this density. Okay, so in question it will be described what is this density. So we can have the density in polar coordinates and so we can have density in Cartesian coordinate and polar coordinate. So it will be given the density at any point P is given by some equation, or it will be described. So let's say here it is point P and it is represented by x comma y. So this point is x and this point is y. So the density at point P is at a distance of root of x square plus y square from the origin. Okay, so you have to remember this point P can be any point in the plane and we are given the density at this point, so we have to include that density. Similarly, we can have the density described in the polar coordinate. So in the polar coordinate, let's say we have point P in polar coordinate, it will be r comma theta. So this will be our pole, that is origin in this case. So this distance will be r and this will be our theta. Then this distance P from the initial line is nothing but r sine theta. Just remember this will be more useful when we solve the problem, because it will be described like the density varies in such a way that its distance initial line is twice its distance from the pole, something like this. Okay, so that's how you have to extract the density from the question and you have to find the mass using this formula. This will be more clear when we see the problem on this. So let's take one problem.